In this video, let's talk about the concept of exponential and logarithmic functions. You have seen that a lot is written on the board. You don't need to panic and worry. We'll be taking up all of these things one by one. First of all, the word is exponential and this word is logarithmic that we have to talk about. Let's keep it clear in our mind. We have seen how to differentiate exponential functions and logarithmic functions. We know that the differentiation of e raised to the power x is e raised to the power x only, the differentiation of log x is 1 by x only, and so on. Now basically this video concentrates on the actual real meaning of the exponential and the logarithmic functions. Let's study it by graph because observation makes things more clear than words. So the graph is given and this graph has nothing but y is equal to x, y is equal to x square, y is equal to 10 raised to the power x plotted on it. Y is equal to x will be a linear function, y is equal to x square, a polynomial function, y is equal to 10 raised to the power x, an exponential function. You observe that here we have plotted 0, 1, that means the x coordinate is 0, the y coordinate is 1. Here it is 1, 1. 1, 1 means what? 1, 1 means that I have the x and y both coordinates as 1. And you see that this is 0. Whenever we have to plot y is equal to x, it is a straight line and it is inclined at an angle of positive 45 degree with the x-axis. The slope is 1. So this is y is equal to x. You talk about y is equal to x square, it goes somewhat like this. It becomes steeper and closer to the y-axis. And when talking about y is equal to 10 raised to the power x, an exponential function, it passes through 0, 1 and it goes about something like this. That means y is equal to x, a linear function, no issues with it. We know how to draw it and how to study about it. Y is equal to x square, we observed when the power was 1, the graph was less steep. When the power became 2, the graph became more steep. Had the power been 3, the graph would have been more steeper in turn. So that means the steepness of graph basically tells us what? Basically tells us how fast is the growth. The steeper the graph, the faster the growth. The growth is faster. So the more steep or the steeper, the faster, right? So that we have taken up. Next, what we are going to take up is when the power of the exponential, when the power of the polynomial function, suppose was 1, it was called linear function, not exponential, I'm sorry. When power became 2, it is a polynomial function again. Suppose the power was 3, it became a cubic one. And again, what you would have noticed that the power 3 would also have been something like this, but this time the graph would have been something like here. I am drawing it a very rough one. The power 3 graph would have gone something like this. That means the cubic one would have become more steeper. So as soon you increase the power or the degree of the polynomial, it becomes more steeper. So the growth of the polynomial functions is dependent upon what? It depends upon the degree. This also has been taken up and this graph has been clear to us till now. Now, let's leave this box for now. Let's move to something called as this. This classification, this section of my board is dedicated to the logarithmic functions. We know about log, we know the properties of log, log m raised to the power n, log m upon log n, and so on. So now you see that this is a graph. It shows the logarithmic functions, log x to the base 10, log x to the base e, log x to the base 2. Whenever you have base e, it is called as natural log, that you need to know. Natural log. Whenever you have base 10, it is called as common log. Right. Now, you see that 1, 0 is always there on the graph and whatever passes, it passes through 1, 0 only. When the base is 10, when the base is more, it is nearer to the x-axis. When the base increased to e, when the base decreased to e, it became a bit higher growth, and the base now when changed to 2, it again became more higher. You know that e has some value approximate to 2.7. So when the base was 10, it was nearer to x. Base decreased to 2.7 nearly, became higher in altitude and height. When the base changed to 2, that means decreased more, it became more upwards. So this shows me what? Let's take out the domain and range from this. The domain is what? X values can be what? Log is defined only for positive reals. So the domain, what you can put in X is real, positive reals. But what is the range? You see that the graph is actually, if you see, it can give me any value from up to down, down to up. So the range is all real. So the range is all real. And always 1, 0 is located on it. And when I move from left to right, I see that my graph basically rises. So I was here, I saw that the height of graph was something called as this. When I moved here, the height became like this. When I moved more here, the height increased. So you are moving and you are seeing that the graph rises. So left to right, the graph rises. This is about the logarithmic function. And you see some definition written over here. It says that the domain is real positive, the range is all real, domain, range, and logarithmic can also be related to exponential. Actually, the logarithmic functions and exponential are the mirror images of each other. So if b raised to the power y is equal to x, this is the exponential form. The logarithmic form to it would be y is equal to log x to the base b. That you need to know, right? This is the definition. We are done with this part, we are done with this part. Let's move to the exponential category and the category that yes, logarithmic and exponential are mirror images of each other. Now, you see that when the base was b, it basically became b raised to the power y. So, b raised to the power y gives me x. So, that means I have something called as this, it will be e here, which is the base. So, log x to the base e is equal to y, then we have y is equal to e raised to the power x. The same definition follows. Here the base is not b but e in our question. Now, you see that what happens 0, 1 when we talk about exponentials. So 0, 1 when we talk about exponential. But when 0, 1 was with exponential cases, 1, 0 when we talk about the logarithm, because basically these are mirror images. If 1, 0, then 0, 1, the mirror image. So 0, 1 for exponential, 1, 0 for logarithmic. Exponentials approach is towards x-axis. Logarithmic's approach is towards y-axis. These are basically the mirror images of each other. Now, because we have seen this, I can also tell you when we move from left to right, what we see, the graph's height increases. When we were here, the graph was only this much. When we moved here, the graph increased this much. So, moving from left to right, the graph's height increases, right? Here we have written something about exponential functions. You see that exponential, e raised to the power x, what value of x you can put out? You can put any value, positive, negative, any value. So, exponential domain is real, all real. And what about the range? The range, it is giving me only the positive values. So, the range is what? The range is real, which are only positives. So, positives real. Suppose e raised to the power minus 1. Although x is negative, but it is giving me what? It is giving me e raised to the power minus 1 means nearly 2.7 raised to the power minus 1. 1 upon 2.7. Again positive, right? So, it is like this. And for very large values of x, for very large values of x, what will happen? My function is very close to 0. When you have very large values, you see that the function lies very close to 0 on the x-axis, but it does not meet 0 at any time. So, this is all story about the exponential and logarithmic functions. You can always know that what are exponential, what are logarithmic, and then solve the questions based on it.